So why would we want to use logistic regression? So we have many important research topics where the problems we have will encounter dependent variables that are really limited, and we'll look at some examples of that on the next slide. And so sometimes we can use binary logistic regression, which is a type of regression analysis where the dependent variable is a dummy variable that's coded as 0 or 1. So logistic regression is going to be similar to regular regression in that you have your coefficients and your predictor variables to determine an outcome. But with regular regression, your outcome variable is a continuous variable, while logistic regression has a categorical outcome variable. And for the purposes of this discussion, we're going to look at binary logistic regression, where your outcomes can either be 0 or 1. And so some situations where your logistic regression would be appropriate is, like I said earlier, when we have a limited set of responses that the predicted value can take on. So if we're looking at modeling voting behaviors, morbidity, or some other discrete variable, like I said, we're going to focus on binary logistic regression for the purposes of this discussion, where our outcome variable can only take on the values of 0 and 1. And so the example we're going to look at is evacuations before Hurricane Harvey hit. And the question was, did you evacuate your home to go someplace safer when Hurricane Harvey hit? And the responses could be yes, no, do not know, or refused in this case. And what was done to evaluate these responses is that all of the responses that were yes were coded as 1, and all the other responses were coded as 0. So we're going to make the assumption that if the responses were I don't know or they refused, that they would be in the no category. And so this ends up with a situation where we had yes or other as our response types. And so here's a sample of the data from our hurricane evacuation file. And as you can see, there were several other characteristics here of our individuals to predict whether or not they evacuated, including whether they have pets or not, or whether they lived in a mobile home, how long they lived in that home, that would be the tenure value, and the years of education they have. So tenure and years of education are both continuous variables, and then our first two variables are going to be our categorical or dummy variables. And so if we were to take this data and run an ordinary least squared regression, this is the output that you would get if you ran it in SPSS. You would get the same answers if you ran this in a different statistical software package as well, but SPSS was used to generate this output. But when I get an output like this, the first thing I'm going to check is my global test, and that's also known as your omnibus test. And so that's going to be looking at your F statistic from your ANOVA table. And what this F statistic is doing is it's evaluating if your independent variable has coefficient values whose differences from 0 is statistically significant. And typically you're going to use this at the 0.05 level or the 95% confidence level. Here we see that our global test is statistically significant, and so that's going to indicate that at least one of my predictor variables has a slope that's statistically different from 0 at my 95% confidence level. Now I'm going to move on to my coefficients table and look at my t-tests. My individual t-tests are testing whether or not the individual slopes are statistically significantly different from 0. And you're still going to keep your significance level at 0.05. So here I see that all my predictor variables are statistically significant at the 95% confidence level except for education. So at this point, we don't have anything that really raises any red flags. And so you might want to say, here's my predicted model for this data and then move on. However, you do need to still evaluate the other assumptions of regression to make sure that your model is appropriate. So here, when you continue to assess if your regression model makes sense to model your data, you'll notice that you have predicted values that go outside of the 0-1 range. However, whether you evacuate it or not is going to be a 0 or 1 situation. The probabilities you should predict should be between 0% and 100%, or between 0 and 1. But in this case, we get predictions that are outside of that 0-1 range because of how we came up with our regression equation. Furthermore, when you look at the probability plot here on the left, this is what we see. we have some significant deviation from what we would indicate as a normal probability plot. So a normal probability plot is going to be really close to this 45-degree angle line. And so remember, one of the assumptions of linear regression is that our residuals are normally distributed. And so that would result in them following a straight line if they were normally distributed. So here we see an S pattern, and that's indicating that this assumption is not supported. Then, in the next plot on the right, we can look at our standardized residuals versus our predicted values. And here we're assessing the assumption that the observations are independent. And here we see, a little bit of a pattern. And typically we expect to see complete randomness. So this odd behavior here tells us that we have a clear pattern and is an indication that we're violating several assumptions of ordinary least squares regression. And therefore that output that we saw in the previous slide is going to give us some significant bias in our estimates and isn't going to be very useful. So we need to look at a different model. This is where the general linear model comes into play. There is a way of solving these problems where the resulting models that we're using are called generalized linear models. A logistic regression is just an example of one of those types of GLM type models. All GLM models have our following characteristics. So we have a probability distribution describing our outcome variable. There's a linear model where you have an outcome, and then it's made up of the linear composition of multiple variables, including the intercept and your beta coefficients for your X predictor variables. We have a link function that relates the linear model of the parameter of the outcome variables. Our GLMs do not use the same methods as we did in ordinary least squares regression to minimize the sum of squared errors. So what we're doing here is we're using the maximum likelihood estimation to estimate these values rather than our ordinary least squares regression approach. The starting values of the estimated parameters are used, and the likelihood that the sample came from the population with whose parameters is then computed. And then the values of the estimated parameters are adjusted iteratively or at each time until the maximum likelihood of the value with estimate parameters is obtained. So the maximum likelihood approach is going to try to find the estimates of the parameters that makes your data that you actually observed also be the most likely label for this type of approach. So let's talk about the maximum likelihood estimation for a bit. Basically, the maximum likelihood approach is designed to find estimates of parameters that make the data that's actually observed be our most likely approach. And so it's also set to find the combination of coefficients that's going to result in the log of the likelihood function being as large as possible. And so you might also think about it as a way of finding coefficients that make -2 times the log of the likelihood function as small as possible. This function is set to find, we're following the condition where y is minus the p of y equals 1 of xi equaling 0. So we sum that over all of our observations of, 1 to however many we have. So for step 1 with the logistic regression response, we want to consider using the logistic regression approach for our evacuation scenario. And so logistic regression equation uses our P to indicate the probability of an occurrence belonging to whatever class you've labeled as 1. And your probability value needs to be constrained between 0 and 1. And so as we've seen with regular regression, the outcome variable can be any value and is not limited to any range. Logistic regression is a generalized linear model that is used to model binary categorical variables using numerical and categorical predictors. Similar to ordinary least squares regression or multiple linear regression, we can use continuous or categorical variables as my predictors. We can assume a binomial distribution is produced by the outcome variable, and therefore we want to model the P, or the probability of success, for a given a particular set of predictors. To finish specifying that logistic model, we're going to need to establish a reasonable length function that connects your left-hand side of the equation to your probability. We have a variety of options, but the most commonly used one is going to be the logit function. And the logit function is looking at the log of p being equal to the log of the odds. Again, where odds are p divided by 1 minus p, and your p needs to be a value between 0 and 1, or between 0% and 100%. So the criteria here for a generalized linear model where we're using the binomial distribution is we assume that the y variable, or the outcome variable of being whether they evacuated or not, follows that binomial distribution with some set probability. And then we are setting this function where eta is equal to beta 0 plus beta 1 x1. And we're, whatever predictors we have. Okay, and then the logit of p is what gets substituted for our eta value. So this becomes your logic or log odds of that event. And then from here, we can actually arrive at your probability by looking at the exponent of whatever is inside your logistic regression equation divided by 1 plus the exponent of whatever's in your logistic equation. And then you can fit and create estimate probabilities of evacuating from each observation using your logistic regression approach. Then you're going to calculate the odds. So odds are another way of quantifying the probability of the event. This concept is commonly used in gambling, and we'll see in logistic regression where our odds are calculated. And if you're looking at the probability of event occurring divided by the probability of event not occurring, which just made 1 minus that probability, or also known as the complement, right? So if we know the odds, we can calculate the probability by taking the odds of the event occurring divided by 1 plus the odds of the event occurring. Our odds ratio looks at the relationship between the probability of an event occurring versus it not occurring. So if we have a 75% chance of rain, and that means that we have a 25% chance that it's not going to rain. So the ratio of these two values gives me 3 to 1. And so that's kind of when we're talking about betting, and I say that the odds of this are 3 to 1, that means you have a 75% chance of whatever you're betting on happening versus not happening. So since we have these two equations to calculate the probability, we can set them equal to each other to be able to relate the odds back to our regression function. And taking the log of the odds and the log of the regression equation gives us our logit function. The logit function is a linear function of predictors that can be any numerical value, so we need to be familiar with the relationship between the logit, odds, and probability. So here in our top graph, we see that the odds are demonstrated as a function of p, and then we look at the bottom graph that shows the logit as a function of p. So notice that the odds can take any positive value or 0 when we're looking at a logit value being any real number. The assumptions for binary and logistic regression are a little bit less restrictive than we have with the other general linear model, and they are as follows. So our outcome variable needs to be dichotomous, meaning yes or no, 1 or 0. Scores on the outcome variable must be statistically independent of each other. It's important that the model only includes relevant information and leaves out irrelevant information, and the participants in the study can only be classified as a member of one group and not the other. Logistic slope coefficients can be interpreted as the effect of a unit of change in the x variable on the predicted logits with the other variables in the model held constant. So what this means is, how does a 1 unit change in x affect the log of the odds when the other variables in the model are held constant? So now, when we're interpreting these odds ratios, we have to be careful at how we look at this because they're a little bit different than what we've seen with ordinary least squares regression. The logistic slope coefficients can be interpreted as the effect of 1 unit change in the x variable on a predicted logit with the other variables in a model when everything else is held constant. And so that's how 1 unit change and x changes the log of the odds when the other variables in the models remain the same. So let's look at this a little bit further. The Logit model solves the problem for when we're looking at our evacuation problem, right, by looking at the log odds, which is p divided by 1 minus p. And you're solving it by setting it equal to alpha, your intercept, and then plus your beta x plus some error. And again, the length function we're going to be using here is our binomial distribution. And so once again, here we have p being the probability that event y occurs, which in this case would be that the person evacuated. And then we have p divided by 1 minus p being our odds ratio. And then we have the log of the odds, which is called the log odds, or often referred to as our logit. As the logistic distribution constrains the estimated probability to fall between 0 and 1, as a result, standardization is not going to be required for logistic regression. That is, again, one of the flaws that we saw when using ordinary least squares regression with this type of problem, is that we could have solutions that were outside of the range of 0 to 1. But by using logistic regression, we can constrain the outcome to be between 0 and 1. And so here we get our estimated probability here, where we have p is equal to 1 over 1 plus e raised to whatever your logistic regression equation is. And so if we let alpha plus beta x equal 0, then your p is going to equal 1. And then if alpha plus beta x gets really small, your p-value is going to be equal to 0.5. And then as alpha plus beta x gets really big, your p-value is going to approach 0. And so then the probability, again, is going to be bounded between that 0-1 constraint. And again, to summarize the benefit here, one of the reasons why we want to use logistic regression is that ordinary least squares can have values outside of our 0-1 range, which would make it theoretically impossible and also lead to various violations in the ordinary least squares regression assumptions, therefore making your model biased. So it ends up making your parameter estimates biased and not very useful. So by using the logit model, we can constrain the probabilities to fall between 0 and 1, causing it to follow this S-type of curve where we're estimating the actual probabilities using that logistic regression approach. An important property of our odds ratio is that they're constant, and so it doesn't matter what values the other independent variables take on. So for example, you say you estimate the following logistic regression and you come up with negative 13.708 as your intercept. And then we have a positive 0.1685 x1 plus 0.0039 x2. Okay, so the effect of the odds of 1 unit increase in x1 is going to be the exponent of the coefficient, which in this case is 1.18. And so what that means is that the odds increase by 18%. So 1.18 minus 1 is where we get that 0.18, which is your 18%. So therefore, a unit increase in x increases your probability by 18%. 1 increment increase in x1 increases your odds of by 18%, regardless of the value of x. So whether you're starting at 0 and then going to 1, it's going to increase 18%. Or if you're going from 999 to 1,000, it will still increase by 18%. So that's something to keep in mind when you're looking at interpreting your odds ratios. So you could complete the logistic regression evaluation of your evacuation data. And so if we were to look at this output, the coefficient, sometimes the beta or the estimate, will be the value that you would see in your equation. And if you take the exponentiated beta value, you'll be able to determine the likelihood of a positive outcome for individual variables. So for instance, if we look at pets, we have a coefficient of negative 0.640, but when it's exponentiated, we get a value of 0.527. And so what this means is, if you look at that value, the exponentiated variable for pets being 0.572 tells me that households with pets are 0.527, so they're less likely to evacuate than those without pets. So if I'm looking at mobile homes and I've got that exponentiated value of 4.885, this means that people that have a mobile home are almost 5 times more likely to evacuate compared to those with brick and mortar homes. So the other thing we can do is we can get some output here on the significance of our predictors. Here we have the different predictors for the model, and you can see that there's not a z-task similar to what we have with the ordinary least squares regression. But what we do have is the Wald chi-squared test that looks at the unique contribution of each predictor in the context of our other predictors. So what that means is, by holding everything else constant, how effective or how much did this predict or contribute toward my overall model? We can interpret the p-values the same way we've always done before, with p-values less than 0.05, indicating statistically significant predictors. So, for example, here we see that predictor pets has a p-value of 0.001. This would indicate that it is a useful predictor for predicting whether an individual would evacuate due to Hurricane Harvey or not. You can see that there are all significant here once again, except for education, just like we saw before with the OLS regression. But yeah, the level of education was not statistically significant contributor towards the model, and therefore we can determine that it wasn't a useful predictor. We can look at it here as an output if the lower and upper ranges on the odds ratio. So if you exponentiate your coefficient, now you get your odds ratio. And if you take the exponent of the coefficient for pets being negative 0.640, you will get 0.527. And then again, if your odds are less than 1, that means it decreases the probability that you will evacuate. So if your odds ratio is above 1, generally that would indicate that your probability of moving or evacuating are going to be higher. So based on these results, you're going to be more likely to evacuate if you live in a mobile home. But if you look at education with an odds ratio of 1.058 and look at that 95% confidence interval, what we see here on the right of our graph, we see that upper and lower range. You can see that it ranges from 0.996 to 1.159. So you see that this value includes 1. Remember, if the odds ratio is 1, that means it can go either way. So it's not really very useful to use this as a predictor to try and differentiate whether your odds of actually evacuating are higher or lower based on your education. So, one of the things to kind of keep in mind, or the takeaway message on that, is if your predictor variable has 1 in its confidence interval, it's probably not going to be a very useful predictor for you in logistic regression. So looking back at what we're doing with ordinary least squares regression, if that confidence interval included 0, then we would say that it's not a useful predictor. But when we're looking at logistic regression, when we look at the odds, which is the exponent of your coefficient, if your confidence interval of your odds includes 1, then we say it's not a useful predictor variable. So now let's go back and practice calculating probability and odds from this example. So our question is, what's the probability that someone without pets who has lived in their brick and mortar home for 20 years with 18 years of education, what's the probability that they evacuated? So here we get the equation where our logit is equal to negative 1.015 minus 0.640 times pets plus 1.586 times mobile home minus 0.020 times tenure plus 0.057 times our education. And so when we substitute our values into our logit equation, we get this value where logit equals negative 1.015 minus 0.640 times 0 plus 0.1586 times 0 minus 0.020 times 20 plus 0.057 times 18 to get a value of negative 0.389. Now, to calculate the odds of evacuating, we're going to take the odds and then exponentiate our logit. So if we exponentiate negative 0.389, we're going to get 0.677. And remember, it's a good idea to keep this value in your calculator or your Excel sheet and just refer back to that value instead of rounding your values, so you can reduce the margin of error in your calculation. And then finally, we can calculate the probability of evacuation. So the probability of evacuation is going to equal our odds over 1 plus odds, which equals 0.404. Since the model is coded with evacuation being 1, this means that the probability of evacuating was less than 0.5. So that means that we could classify this individual as being one who would evacuate. And the probability that they did not evacuate would be 1 minus 0.404. So when working with this type of problem, you want to make sure that you're paying attention to how the model is designed and what the question is asking. So we have a 0.4% or a 40% chance that they would evacuate and about 60% chance that they would not evacuate. And so if we were using this maybe in a classification model, since this didn't quite pass that 0.5 threshold, you might classify this as an individual who did not evacuate. But looking back, what we're looking at with ordinary least squares regression, remember going back, thinking on what's going on with our confidence intervals. Once again, if it's regular OLS regression, if it's including 0, we're saying, if the confidence interval is not including 0, we're saying it's not a useful predictor. But with logistic regression, if your confidence interval includes 1, that's going to tell me that it's not going to be very useful for